Alright, time for another draft. Physics.com, debatephysics.com also. But very little in the form of any useful or rational or, connected to anything called evidence kind of debating. But anyway, I can only do my part, okay, which is to explain how, science is supposed to work, where you gotta let the facts lead the way, okay, not the wishful thinking. And in this case, I don't know why everybody wishes the universe to be a bunch of nonsense, but apparently that's what everybody likes, is nonsense. I don't know. All of this is really not that hard to deduce. The fact that they're pretending, oh, it's so hard to understand. No, it's not really. So I have been, did make a video for a couple of days, been kind of researching neutrons mostly, and Rutherford, and it's sort of interesting that, he doesn't say much that I find silly or stupid compared to the rest of them, and so it's kind of, anyway. The observation is, okay, so why did the neutron get called a neutron? I guess I could argue. So they knew this thing was more powerful than a proton, and that's about all they knew. They knew something was popping out, and it appeared to be, kind of thing. And that's all they could really go by, is appearances. Because they don't, they didn't have instruments that can do anything precise in terms of taking a photograph of anything or any of that kind of stuff. So, as I understand it anyway, what they do is they take a piece of some kind of radioactive stuff, radium or something, and they allow that radiation, the alpha, the big helium nucleuses, to plow into something. So that's a lot of energy, and that breaks it up. So that's the first particle atom smasher. It's this crude version. So they just allow a radioactive substance to irradiate something, and then that causes that substance to radiate something. Okay, so it's that's kind of how they created these effects that they made these assumptions about. And so anyway, when a neutron pops out, the idea is they're saying, oh, it can't be bent by a magnetic field, and I can explain that. All right, so this is what what has occurred to me. All right, so I sort of pointed out that if you put an electron and a proton, really close together, you're going to have what's basically a perfect dipole. Okay, so I could have drawn these as circles. It doesn't really matter what shape they really are. And the idea is, oh, Jesus, green's wearing out already. It's always the green. Well, I'll try to ignore it. Anyway, and so it's this is really the only pure dipole. All the other dipoles, that is, all the things we call a dipole, even when we draw magnets, we draw this kind of thing, and it's really a lie. It's really not the truth, because they're not perfect dipoles. It's a complex dipole in the sense that it might be looking something like this. Okay, and we'll call it a dipole because it's obviously got more of this, green, on one side than the other. But you can clearly see that there's still access to the opposite pole. It just depends on position. All right, and so this is the whole argument about what a nucleus is. A nucleus is something that's got a lot of poles. It's got places that look very negative, and it's got places that look very positive. And that's the niches that the extra electrons, the exterior electrons, as Rutherford called them, and that's what I called them, that's the niches they fall into, are these little extra places where the protons are still quite visible, but there's electrons, okay, that are obscuring the perfect view. And they're locked in those positions, and all they're doing is, they're vibrating in those positions. Those are the orbitals that they, make as this wooey nonsense that it has a probability of being somewhere in there. Well, yeah, it has a probability of being somewhere within this wobbling zone. Now, I don't think the wobbling zones are anything like what they draw because it's huge. You know, they have these gigantic areas that it could be in, and guess what? It's never here, and it's never here, and it's never here. All right, it's always somewhere, you know, pretty close to the same place. It's just vibrating in those places. Okay, everything is vibrating because everything has some kind of temperature, because everything's interacting with everything, and it's all a bunch of tension that everything is in. And if the little proton moves down a little bit, then everything else here has to move, has to adjust to the new position. And so that's all of this wobbling and variance. So anyway, the important point is there's only one pure dipole, and that's the neutron. And the reason why, okay, it appears to be neutral is because the only way you can push this neutron is you have to push it this way, or it's not likely to go anywhere. If you push it from the sides, all right, and I've already established, frankly, you know, by my rules anyway, you can understand that the force can't affect both of these the same way. So the same force coming in, you know, green or red, wouldn't affect these two things the same way, so they're not going to be pushed by a wind this way, crossways. And the fact is the only way they can really be pushed is you have to push in the direction of their orientation. And if you push them any other way, they'll just turn, okay, or do some other thing. And if they turn and they're inside an atom, then the rest of the atom has to turn. So they're going to push everything else with them. All of that's going to happen. So that's the key thing. So when it's flying through their magnetic field, what's happening is yeah, you're pulling on this side and you're pushing on. There's no need for it to turn because it's being pulled here and it's being pulled here, and then it's being pushed here and it's being pushed here from the other side. So there's just, you know, it's just not going to turn because the pushes and pulls, all right, are against each other in a sense, and it's you know, it's the velocity. See, if I push and turn it, then I ruin its momentum. I didn't really explain that right. All right, let me do it again. All right, so when it's flying and the force is acting on it, the point is that you can't have this velocity and also have the turning velocity. And so what will happen is these two things will move away from each other. They'll move this way and this way. And if they do that, then they start hitting the force differently and the whole thing will just break apart. So to stay together, it has to move, you know. And the point is it's also high energy neutrons. So they weren't observing low energy neutrons at first. The only way they get the low ones is to sit there and put them through another piece of material to take the velocity off of them. And the fact is then they can add them, which is sort of interesting because this gets to the alchemy part, because now they can take a slow moving neutron and they can add it to another substance and make an isotope, because they can actually inject the neutron into the nucleus. So they can make they can change the nucleus of an atom, but they can only do that with a slow, you know, the slower they're moving, the more likely they're able to do that. The faster it's moving, the more likely it is to cause the opposite effect of the nucleus splitting. So anyway, it's getting more technical than I want to. The point is that with a velocity this way, it can't keep going this way if this orientation changes. So it's got enough speed going this way that the ability to turn isn't strong enough. The magnetic field you're creating isn't strong enough to cause it to flip. So it's not turning, and it's certainly flipping isn't going to change its direction because its direction is set by this. And turning this itself, this piece isn't going to turn. It's just going to be moved sideways. So this velocity is not going to be interrupted by any movements in these directions, just kind of like the gravity argument. And so you can't change the velocity by making it turn in this case. because it's more complicated because there's two objects pushing on each other. Anyway, it sort of can be understood that if you push on this one, you're not going to be able to push on this one, you know. And the only way you can push both of them is to push them in this orientation. So the point is they don't deflect in a magnetic field, because if you take the total amount of pressure pulling and pushing, it's equal on both sides, and it can just shoot straight through. So it looks neutral, but it's not neutral. All right, well, I spent a lot of time on that, and that wasn't my intention, because I get distracted from all the other stuff that I thought about. All right, so the important thing is the idea that when you're looking at a common magnet or something, it's not as simple as this side is north and this side is south, because it's all a bunch of messier dipoles. So there's a whole bunch of still, just like the nucleus itself has got a bunch of electrons in it. See, that was the part I found interesting, is they recognized that fact back in Rutherford's day, that the nucleus had electrons in it, and they could they could knock electrons out of the nucleus, and they still can now. So why are they implying that the neutron is anything other than an electron and a proton? I mean, it seems kind of obvious that that's the only place the electrons can be hiding is in the neutron. And the neutron's just sort of an arbitrary designation we give to an electron and a proton that are very close together. And the fact that they even had the deuteron, you know, the idea of an electron, a proton, and an electron, or a proton, an electron, proton. So they even knew that concept. So why were they even inventing the strong force? I mean, it just seems, why would they take this knowledge that, well, obviously electrons will stick to protons. Why wouldn't they? The argument is why would they stay separate? That's the part that seems hard to understand. It's not the strong force pushing them, getting everything compact. The idea of why it stays less than completely stuck together is the more obvious question. And obviously that question is answered by the fact that, you know, once you start pushing these things together, it becomes kind of obvious that you can't have them, you can't have this stuck to this, and this stuck to this, and this stuck to this, because then these things are literally can see each other and they'll repel. So because of the nature of the repelling elements, there's no way you can get everything to smash right next to each other unless you order them very carefully, like a neutron star, which, I hate to have to draw all this, but the idea would be is that, see, that was the other thing I realized was about magnetism. I see there's so many little things, you know, and the fact is that there's bonds that are the stronger ones, and then there's the weaker ones, and, oh, I drew that wrong. Unfortunate. This is a green here. All right, and so the idea is that everything's lined up, red, green, red, green, red, green. Okay, and you end up with one side that's always going to be green. So no matter where you break the magnet, it's always going to look green. And this side, because these are the hard bonds, and the superficial ones that look the same but are superficial, right? This would be a superficial bond here, where this one sticks to this one. Alright, you could sort of understand that that's the breaking point. I can't break the neutron, but I can break the connection between the two neutrons, because that's not as good a bond. Alright, because of the structure, that's the one that can pull apart easier, let's just say. And so that's where the atom breaks. So the atoms are breaking. See, the other point is these aren't neutrons, they're atoms. And the atoms aren't a perfect dipole, they're an imperfect dipole. So you can understand that the part that's an atom, a nucleus, the nucleus isn't going to split in half, but the connection between the atoms will split. Okay, so that's a better way to put it. So you can understand why it breaks that way, and it always breaks with a positive end showing and a negative end showing. So that makes perfectly good sense. And it also sells the idea that you still see plenty of the other poles. So there's still plenty, although there's a lot of green being radiated out of this end, there's still plenty of red in there. Okay, And so it's a mixed pattern that you get out of a magnet. And that's why an electron sitting out here, let's say, you would say, okay, it's the opposite of this pole, and why doesn't it just pull right in? And the reason why it doesn't is because these are atoms, and all of the bits are jiggling, okay? And it's not until you get it really cold, right? So we're back to, now we're to the cryogenic stuff. When you get it really cold, then you can have locking. That is, then you can have positions where the electron will stay in that one spot because it's a perfect mixture of the red and the green. But when it's all jiggling, you can sort of understand that the electron's going to get hit by attractive force, then it's going to get hit with a repulsive force, then attractive force, and it's always going to be a mush because everything's moving here inside of this. The magnetism is moving too much for a single electron to see it. But something as big as another magnet can see through that fog or the haze of that jiggling, because it's also jiggling a little bit, but it's big. So the little bit of jiggle isn't going to remove the idea that this is net positive and this is net negative. It also has to do with these vector lines. And so it's the same thing as the fringe patterns in some ways. There's certain places, okay, where the forces add up when you add up everything that's visible, and places where they don't. So there's places where it looks very negative or very positive, and so there's places where it will get a tug, but it'll move from that place into a place where it's getting a push. So it can never get any momentum. Alright. Never keep any momentum. Alright, so that was another point I wanted to make, but I'm not really doing this in the same order I wanted to. But it doesn't really matter. Alright, I'll take a little pause and just think of the other points I wanted to make. Well, it's all... it's not exactly what I wanted to do either. Yeah. I do have to get a better mouse. Quit fucking around. Anyway, be back. Alright, so the point is... okay, the point I wanted to make was that the real point is that magnets and other dipoles, when they call something a dipole, it's not really pure. It's not a pure, you know, it has 10 protons this way and 10 electrons that way. It's always less than pure. And that's what makes it, you know, when you draw it, it doesn't draw the same as if you have a pure dipole. So if you draw a magnet with pure dipoles, it's not gonna, you know, not gonna mean anything, because it's not what it actually is. And like with the Stern-Gerlach experiment, for example, they have an uneven magnetic field, which just means that if it's something's a little bit positive, it's going to move in one direction, and you know, depending on which way it's pointed, and a little bit negative, it's going to move in the other direction. And all you have to do is it's just about which way it's facing. So, you know. So I can illustrate it by saying, okay, this is the dipole, but the dipole really isn't this. Okay, the dipole is something like, you know, this. It's a little dipolar, okay, because it's only when we're talking about an extra electron, and so it doesn't have nearly enough magnetic. You know, it's not nearly enough magnetic to cause it to flip. So it doesn't change its orientation. So you shoot it through the magnetic field. It's got a little extra red, so it'll get moved away in one space, and then, but if it goes in this way, okay, then it's going to go this way, and if it goes in this way, then it's going to go that way, but it's not going to turn to the magnetic field. So all that happens is they shoot these minor dipoles through a magnetic field that's uneven. And they're surprised that they get the result of half of them go this way and half of them go that way, because half of them go in this way and half of them go in that way. And that's all they're really measuring, because they don't flip. Flipping, you have to have a real dipole to do the flipping thing, because you have to have the same force pulling this one as you have pushing that one. And when they're not whole dipoles, the forces aren't anywhere equal. Anyway, and so the flipping thing won't happen as aggressively, and it's a lot more subtle. and so it doesn't have enough effect to change which direction the thing flying will fly. Alright, well, it's more complicated than I wanted it to be, but whatever. Just going, this is the preliminary stuff. So I was thinking about the photon thing, and what, and the ultraviolet catastrophe and all that kind of crap. Let's see. These are neutral atoms. How do I want to draw neutral atoms? I'll just draw them all the same color, I guess. So as I have argued about, it can sort of be seen with at least radio antennas. The idea is that the electricity travels at the speed of light. Okay, it has a limited speed, and through atoms it's slower because it has to hit all of these bits of electron to convey the energy. So the electron motion, okay, it should be understood. The electron isn't going to move very far, but there's electrons, and they all have equal pressure between each other. And you basically are going to cause an electron to move a little bit. That signal is going to go at the speed of light to this one. Okay, so that's happening. C, the force between the protons, is moving the speed of light. So the electron moved 1/10 of the speed of light, something like that. Okay, this moved the speed of light, and then it does this little 1/10 thing again. All right, and then this is the speed of light. So you have a degrade in how fast the signal is moving. So it always turns out that way. I mean, when they actually measure electricity through a wire, it's not going the speed of light. It's going something less than the speed of light, like 70 or 80%. Because it has to do this little bit here. It's this takes time away from the speed that the electricity would have had. So anyway, so when you put electricity in an antenna, it's moving at the speed of light. So this process of pushing on these atoms, which is creating your signal, and that's what's creating the signal that comes out and creating the little bit of gap between these bits. Now the idea with radio waves is you're sending a whole bunch of photons, so this whole clump, because all of these pushed means that it took energy that was coming in that was separated by this distance. Alright, so that's what was coming into the antenna. See, it's just a reflection. You're not, the energy you're putting into the antenna isn't the energy you're excreting. The energy you're excreting is a reflection of the energy you're pushing. So you're pushing electrons out, and that's causing this to reflect back like this. Alright, so that's your radio frequency. So the point is, point I'm going to make is that photons are doing the same thing, and it's just on this much smaller scale. So instead of sending a pulse, see, the point I should have made with the radio antenna is that it's a pulse going up the antenna, the pulse of electricity, and it makes all those atoms, you know, thousands of them, basically reflect something, you know, where you're compressing. You're taking energy coming in and you're compressing it. And so that's a signal. All of the photons in that unit of time of the pulse, how big the pulse is on the antenna. And that's why antennas have to be different length, because some pulses are very big, some pulses are much smaller. So that's all you need, is that pulse. So you need enough antenna for the full pulse to go into the antenna and push. Alright, and so it's just compressing. Smaller antennas will work, but you get less of a signal. Alright, alright, so let's go back to atoms. Alright, so atoms are doing the same thing, and that's going to be the frequency, or the polarization anyway. So when you shoot electricity through, each atom is going to push an electron at a different time. So basically, okay, you'll end up with this distance between the pulses based on the time it takes the electricity to move through the atoms. So I could have drawn that bigger. And this is your frequency, is this amount of distance between the time for each one of these delays. And that's what's giving your photon its distance, its frequency. And obviously its polarization is being created by the fact that it has to go through each one of these atoms. So I was thinking the polarization of light was very large, but it really doesn't have to for different polarization filters to work. So it's not really about how far apart you put your little bars, okay, of different material. And polarizers are just working by having two layers. Okay, so that should be understood. There's one layer of material, and then they put a second layer on top. These little arranged points, and all you're really doing is changing the phase of the light that goes through. So all the light goes through the polarizer. It's just that the phase of this light, okay, is out of phase. So you've taken light and changed its phase. So this one goes through the double layer and ends up here in time instead of here. And this one's doubled up, so this one ends up here in time instead of here. So it's basically changing when the piece of energy is going to arrive, because it's gotten slowed down by going through two layers of material instead of just one layer of material. It's changed its phase. And that's all you're doing, is changing the phase of the little bits. And then you can put the phase back again with another piece of polarizer, or you can screw the phase up even more and change the frequency of the light, essentially. Anyway, point I wanted to make was, yeah, so that's the origin of the frequency, and that's why ultraviolet light that's why there's a catastrophe. In the sense, you can't just heat something and then it produces ultraviolet light, because the problem is this time to get through an atom is, atoms are kind of big and slow. You have to hit a certain number of these electrons, and there's a minimum number of electrons you have to hit to be able to convey the electricity. And the fact is you can't make a tighter frequency, because you can't make the electricity go faster through the electrons. The speed the electricity travels is going to dictate the frequency, and you can't increase the speed, okay, to create the ultraviolet. And so what you have to have is some other mechanism that multiplies the frequency. That is, two layers of electricity, and then the two layers, one layer is producing and the other layer produces, and that way you can produce a tighter frequency because you have more than one layer, all right, producing the current at the same time. So you have a bunch of these, and you have current going through them at different intervals, and now you can produce some kind of higher frequency, because one set of atoms will be pushing, and then the other set pushes at the half phase of the other one, and that would mean you have a photon that's, you know, twice the frequency. So anyway, yeah, so I think that'll work also. So eventually I'll tighten that explanation up, but I think that works as a reason for the ultraviolet catastrophe. And it also provides an explanation for how you know, polarization is just about affecting a photon. It's not about the frequency having to be the same size as the thing you're hitting, the surface. You don't have to have some special, any surface will affect any photon, because some part of the photon is going to be hitting the surface, and so all you have to do is have any part of the photon hit the surface, and you'll end up with a fringe photon, or element of a photon. Alright, which gets me to some other catch I thought of, but I'm not thinking of it at this moment, so we'll take a pass on that. Alright, so I guess I should attempt to reiterate the point I really wanted to make, which was, why did they ever invent the strong force? I mean, once they've established the existence of protons and electrons, why would they not be able to just figure out that, well, if I had an electron and I stuck it between a proton and a proton, what do I need a strong force for? I mean, obviously the proton's going to be attracted to the electron, and there's no problem if they can't see each other. So I guess that's part of the magic here, is they don't they don't consider the matter to be stuck in a field of energy. They think the matter's radiating some kind of force, you know, some kind of field. Some kind of field is controlling it or something. And obviously it is, but that's the whole source of anything it gives back to the universe. It's just giving back what it got. The matter doesn't create anything. The matter just reflects what goes in. And it has an equilibrium, just like the earth has an equilibrium. Everything ends up with an equilibrium. And it has an equilibrium. And, you know, and then they had this whole thing where, you know, they although their orbiting theory, I think, was nonsense, the way they perverted it, I mean, they didn't even evolve it. They said, okay, it can't just orbit because somehow the electron is doing work if it's orbiting, and it's losing energy somehow because it's making some sort of magnetic field. When, no, it's the same, it's always radiating the same thing. It radiates it whether it's moving or not moving. It's still a charge. And all it has is charge, and that's all it can radiate. So if you move the charge, well, you'll get a field that looks like it's moving, but it's not moving. I mean, it's just moving the particle. You're moving what it's reflecting, where the light's reflecting. If I move this pen, the light disappears over here, and it appears over here. Okay, it's not radiating anything. You know that. You know it's just reflecting light. So what work did the pen do? It didn't do any work. So anyway, and then they just create these magical orbitals that all of a sudden it can orbit as long as it's in this special orbit. And now they basically have changed this orbit into something that's oscillating back and forth here, you know, and creating some woo field, you know, which is probably closer to the truth, but I'm just saying it's still wrong. These things are stuck. I mean, why would they not understand? If I have a bunch of charges and I put them together, it's like a little north-south. It's like little north-south, north-south, north-south. It's little monopoles of magnetism. And you can understand, you can arrange magnets in configurations that, you know, where everything's just fine. You have a north here, and a north here, and a north here, and a north here, and a positive here, and it all fits. And all you do is jiggle it a little bit, you know, and the whole thing falls apart, and they all jump into each other because they all flip. But if you had magnets that can't flip, you can understand it'd be very stable. So I don't know. I just have no. I don't know why they already knew this existed. Okay, I mean Rutherford named it the deuteron. Why would they think that needed a special force to create that thing? I have two protons really close to each other. I didn't need a strong force to smash them together. And again, the simple argument is if I put some high-speed particle into here and I smash into this and I knock this out of here, well, then the two charges are going to be very close to each other, and they're going to generate, you know, by my theory, through the fact that there's still a bunch of green force going in here and a bunch of green force going in here, that'll be converted into red force, and they'll be very reflective very quickly and fly apart. Okay. And that's how it's really working, you know. All right, so I wanted to talk about a little bit about relativity, just because it's just such crap, and this probably won't be another debunk. I mean, it probably won't be good enough to, you know, to mean anything to these morons. But all right, the simple statement: light always travels the speed of light. Duh. Okay. So you have a photon. It's going to travel from A to B at the speed of light. And let's say B is a real place. It's going to arrive at a real place. And then there's some notion that no matter how, so if I decide, I know a photon's coming, and when it shows up, I decide to go, you know, half the speed of light. All right. And I'm still going to see this photon traveling the speed of light. So even though I'm going in the same direction it is, we're covering the same space in a sense, and the photon's covering it twice as fast as I am, but it's obviously 1/2 the speed of light from my perspective. I mean, and if I was able to go the speed of light, obviously I could just keep looking out my window, and the photon, I'm keeping up with it. And, you know, but this idea that somehow the photon arrives at X, and say I was going 10% of it, and I arrive, okay, exactly, you know, 10 times slower. that somehow I'm going to have this huge difference in I've aged differently somehow through the trip merely by going slower than the speed of light. And if I went as fast as the speed of light, somehow I'd be even more time dilated. So even though the photon got here, just normal universe, everything's just fine, somehow I travel the same path because I matter, somehow time changed, okay? And I arrive surprised that I'm there so quickly, and I'm younger than I would have been if I traveled the distance at some normal speed. All right, so I'm not really putting this very well. I just mean, why are people so willing to give up on the idea that there's 3 dimensions of space? Physical space has 3 dimensions. There's things in places in space, and you can't change any of that. But it doesn't matter how fast I go. I can't change actual time. Yeah, you can break a clock. I mean, why can't they even wonder about the idea of, well, are radioactive isotopes the best way to tell what time it is? I mean, is that indestructible? When I can just explain that, no, all I do is put more isotopes next to each other and I change how quickly they decay. So it's easy to screw around with that clock. And, this idea that somehow, velocity makes it decay slower. Well, that's not hard to imagine. Well, anyway, and then we're back to the arguments about what gravity's doing and why it's our clock that's too slow, right? The thing moving 25,000 miles an hour, the satellite, isn't the one that's got the velocity problem. We're the ones with the velocity problems on Earth. It's our clock that's the one that's time dilated, okay? And that's the irony of the subject, is that we're the ones moving too fast. And we're moving too fast because we're being jiggled in gravity. The satellite's being jiggled less. We're being jiggled a lot, which means we traveled a lot more distance, in fact. So even though our linear velocity, it's like hiding angular momentum in wheels. Our linear velocity looks like it's a certain amount. But the fact is, because we're going up and down, you have to add up all of that distance. And that's the real velocity. The basketball has a higher velocity than the basketball player. Okay. Yeah. Is there anything? Yeah. I guess I'll just, I'll have to work on that better. But I just mean the idea that two things are going in the same direction, and you're going to say one thing is always going to look like it's going the same speed is just silly. Frankly, I don't know why people are so willing to believe this crap on such thin evidence. But anyway, and give up on 3-dimensional space. I just don't know why you would be willing to just. It's just so obvious, that it's real space and it takes real time for things to travel in the real space. I just don't know why you'd mess with that. Why you'd be unconvinced, that's a perfectly rational way to understand the universe, is that there's positions in absolute space and there's no need for any idea that you can warp the space or the time. All right, anyway, it's probably enough. Yeah, it's whatever. It's just a video, probably partially for my own purposes. So I'm just giving you the opportunity. You can view it at your discretion. Obviously, you've already viewed it, and so I can't really fix that if you're disappointed. But yes, I'll improve these arguments. This is the draft part. That's why it's called draft physics. So I'm drafting it right here in front of you. Yeah. All right, anyway, till the next time, it's such.